All right, in the following function, are there any particular values of x that we should be concerned about? X can't equal 1, that's right. Why not? What would be 0? The denominator would be 0, and what happens then? The world blows up. You can't divide by 0. We haven't learned how to get around that yet. We can, but you can never actually divide by 0. So in that function, f of x equals x cubed minus 1 divided by x minus 1, x can't equal 1 because of the division by 0. The function is what we would call discontinuous there. As a vocabulary word for you, we're going to be talking about discontinuous and discontinuities a lot, especially in this chapter. The function is discontinuous there because you can't divide by 0. And right there, you would have division by 0. We need to know what happens as x, what we say, approaches 0. That's what that arrow means. As x approaches 0, in order to be able to fully describe the function. So what we're going to do is we're going to start analyzing functions that have discontinuities in them, like division by 0 at x equals 1. And we're going to analyze those things graphically and numerically, and then eventually algebraically, so we can say what happens at that discontinuity. So that's why we need what we call limits. And hopefully in your pre-calculus class you studied limits a little bit. The limit means what happens as we get closer and closer and closer to something important like a discontinuity. Well, the function is getting closer and closer to some certain number, fine. Or maybe it's getting closer to an asymptote, so it's going off to positive or negative infinity, fine. But that's what we're going to be doing in this chapter. If we find the limit of a function as x approaches a discontinuity, then we can describe its behavior. And once we know a function's behavior around that discontinuity, then we can deal with that function appropriately. So if we graph the function, we can see what's going on, and that's called a graphical analysis. Pretty straightforward stuff, all right? Turns out that I have that function graphed, but I want you to do that as well on your calculators. So go ahead and graph that. Whoops. So here's my graph. Notice that the calculators that we have, the TI Nspire CXs, will display the correct format for the equation that you entered in. If you don't see that specific equation, then you entered something wrong, and you probably need to enter some parentheses or something around, put some grouping symbols in on things so that the actual division happens correctly. But there's our function. So let me hide this real quick and go to the next page. That's my function again right there. We know that there's a discontinuity here, but where is it? Do you see it? No, you don't see it. The calculator will never display this type of discontinuity because it can't. Because no matter how much you zoom in on that discontinuity, it always looks like there's points around it that, and actually there are points around it that are going to be graphed. You can never zoom in enough to see the actual thing that is here. So I don't know how that happened, but here we go. Where is the discontinuity? At 1. So when x is 1, we go up to our function right here, and there should be nothing there, right? That's what we call a hole. So I'm going to represent that hole with an open circle there. All that means is there isn't anything there. It's not a vertical asymptote, it's actually a hole. What type of discontinuity is this called? It's a hole. How do we represent this? A little open dot right there. The discontinuity is at x equals 1. Now what value of the function does it look like the function is at? What value does it look like the function is at when x equals 1? Looks like it's at 3, right? So if the hole wasn't there, then we would be able to evaluate the function and wind up with 3. And this is how we're going to start to learn how to get around division by 0. It sort of looks like the function should be 3 when x is 1. So we could maybe say the function is 3 when x is 1, even though we know it's not. So we're going to write 3 here. How do we write this mathematically? Well, I need to talk about that for a second here. As we approach this thing from the left-hand side, we're going to be seeing this quite a bit in this class. As we approach that hole from the left-hand side, it looks like the function is getting closer and closer to what? 3. As we approach from the right-hand side, it looks like the function is getting closer and closer to what? 3. So basically, as we get closer and closer to 1, it looks like the function gets closer and closer to 3. And that's where the limits come in. How do we write this mathematically? We would say the limit as x approaches our discontinuity, which is 1. So as the x value approaches 1, the function, which was x to the third minus 1 divided by x minus 1. So the limit as x approaches 1 of our function, which is written there, equals 3. Hopefully that makes sense. Make sure you understand the language that's going on here, and when you see this, don't think to yourself, LIM x arrow 1. Think the limit as x approaches 1 of. Read it correctly. Okay, so we did the graphical analysis, now we're going to do a numerical analysis. We already have the equation entered into our calculators, so on your calculator, go to table. This is table set is for the TI and not Inspire, the TI 83s. What we're going to do instead is go to menu. Anytime you want to do something on a calculator, you're going to go with menu, and then we're going to go to view, and then we're going to, why does it keep doing that? Okay, show table. So for me, mine is actually, for some reason, number 7. No, it's not. What is going on? All right, so notice that right away, mine came up with this undefined part right here at x equals 1, right? Did yours? Okay. What we want to do is not use that. We want the table to actually show us something meaningful. So we need to menu, it looks like for me it's probably going to be, yep, that. I need to bring this window up. For you guys, it's going to be menu 5. Our table start, we want our table to start where the discontinuity is. So for us, that's going to be 1. The table step, we want to be small. We don't want to go in increments of 1. So let's go with 0.01. Independent, dependent, auto is fine. You can leave that alone. So now I have this table here, and I can actually draw a table on there. Let me go back to this here. Go to table set, blah, blah, blah. We did all that. Use the table to see what the function is doing as we approach x equals 1. Huge point of the day. For a limit to exist, we must be approaching the same number from both sides. In our function. So it's not the x value that we're approaching, it's the function's value that we're approaching. Can we take the limit as x approaches any number? Probably. Yeah, the answer is yes. You can take the limit of any function as x approaches any number, but most of the time we're only concerned about when x is approaching a discontinuity. So let me bring this back up. We can now copy down our table here. So 0.97, 0.98, 0.991, 1.01, 1.02, 1.03. So 0.97, 0.98, 0.99, 1, 1.01, 1.02, 1.03. And then copy down the values from your calculator into that table. At 1, we have undefined. If the numbers that you write down appear to be approaching the exact same number from both sides, then your limit is that number that they're approaching from both sides.